Expert Disk Transfer Techniques, Emphasis 101. So we're just flowing right along here. This is great. Our presenter is Stefano Sergio Cavaglieri, and I hope I didn't mangle that too badly. And Stefano is the Chief Technology and Information Officer of the Swiss National Sound Archives, which is part of the Swiss National Library in Lugano, Switzerland. He holds degrees in electroacoustics and computer science and serves as an active member of the technical committees of AES, ARSC, and EASA. Beginning in the audio engineering field in the late 1970s, he spent several years involved in a variety of audio productions, culminating with a series of world-class recordings and events. And in the late 80s, he broadened his interests to include computer science, first in networking and systems management, and later moving into software design and digital storage. He's now recognized as one of the leading technical authorities in the multimedia archives community, and in 2011, he was awarded the James A. Lidner Prize for his contributions to the field of technology for the preservation of recorded sound. Stefano.
So thank you very much for the introduction, and sorry for this little delay due to some technical issues. Emphasis 101, when I decided to present this topic, I went through a lot of publication that you can find on the web, that you can find just everywhere, talking about equalization and stuff like that. And by the way, one of the very good articles I found during my research was the one written by Gary Gallo about 20 years ago, if I'm not wrong, which is called Record Equalization Demystified. What's the difference between the things that you can find online and this presentation here? The main difference is that I've tried to take all kind of cutting as well as replay or playback devices into account, including optical retrieval systems such as IRE or visual audio, these systems. So, you're all familiar with the re-recording principles. Basically what we are aiming to is we are trying to match the specs of the recording in order to get an accurate playback of your record. So re-recording is kind of an art and science, because there is a scientific part in it, but there is also an, let's say, artistic part in it, which can barely be controlled. If we look at the equipment, the necessary equipment for, let's say, a mechanical playback versus, on the right side, an optical playback, you see that we have a number of components, and some of these components are particularly affected by what we are talking about today. What is underlined, it's mentioned there, what is underlined is, to try to match the specs of the recording. For example, when we talk about stylus or phono cartridge, we have a choice of styluses and these kind of things. So, but all this may sound obvious to most of you. Probably some people think that buying a state-of-the-art turntable coupled with a state-of-the-art preamp or phono preamp coupled with a state-of-the-art AD converter does the job. Not really. point is that we should at least understand a couple of very basic things. When we talk about disc recording, we are talking about a world of transducers. Not only in disc recording, but this is the topic of this speech. So what is a transducer? I'm not going to read it, it's just there. But basically, it is a device that converts energy from one form to another. We have different type of transducers. What we are using typically in disc recording and playback are usually electromechanical transducers. So, at cutting, we run into basically two types of transducers, which have a different response in terms of frequency versus amplitude response. Those in black are basically amplitude responsive. And the one in blue is velocity responsive. It seems strange because if we take electrical cuttings from the very beginning till today, we are 99% of the time talking about, the blue configuration, velocity responsive transducers at cutting. This is what a very conventional lathe does. At playback, similar thing, similar situation. We have several different amplitude responsive devices, which, for example, in the electrical world mean that the physical displacement, the deviation of the groove, just produces a voltage without producing a magnetic flux in the middle. This is, for example, something that happened in a crystal cartridge, a piezo cartridge. They're not very, very used, but there are some around. And this is the same thing that happens in an optical retrieval system or an optical playback system. Let me try to go through some further basic information, which is this one, for example. I've been talking about amplitude. What is amplitude? Amplitude is, as it's written there, the level or volume of a sound vibration or recorded signal. The amplitude is the distance, in this case, between the two red lines. Now, when we talk about an amplitude-sensitive device, especially if it's a playback device, its output, it's proportional to the recorded amplitude at all frequencies. These devices will produce a flat frequency response when playing a constant amplitude recording characteristics, which is, in our case, it is only what we name acoustical recordings. A constant amplitude recording characteristics means that all frequencies are recorded at the same level. So the velocity increases as the frequency rises at the rate of 2 times per octave. So I hope you can see the red line in the middle. So if we look at amplitude specs, the cutting device you know, for a constant amplitude cutting device, the response is just flat, from 20 hertz to 20 kilohertz, ideally. And if we look at the playback response, or the response of a playback device, still talking about an amplitude-sensitive device, it is flat too. So it looks like we are living in a perfect world. No need to change anything. Now, coming to velocity. Velocity is the distance a stylus travels within the groove divided by time. If we talk about a velocity-sensitive device, such as a magnetic cartridge, for example, it produces a flat frequency response only if playing a constant velocity recording characteristics. Okay. Otherwise, the output increases as the frequency rises. So by constant velocity, what we mean is a recording characteristic in which the stylus speed is held constant at all recorded frequencies, which means that the recorded amplitude decreases as frequency rises at the rate of 6 dB per octave. Let's have a look at the response. This is the theoretical response of a cutting device which needs or produces a very high level or a very high amplitude on the low frequencies and goes down to the high frequencies. You see the 6 dB octave drop. When we use a playback device which is velocity sensitive, it does exactly the opposite. So if you take, for example, a magnetic cartridge, the quicker the stylus moves, the higher the voltage is at its output. So if we compensate the previous curve with this one, we get a flat playback, always in theory. Now, the point is that the distance between these 2 points, this here and that on the top, is around 60 dB, which would completely take away all possibilities to have kind of a headroom for dynamics. So somebody invented that technique in order to tame velocity. Because phono cartridges and their amps and stuff can neither negotiate the large groove amplitude that would be required for low frequencies, nor can they properly handle a signal to noise ratio, pre-emphasis is necessary. So what are we doing? At cutting, at recording, we are introducing such an equalization curve, so such a correction, which is in the opposite direction if we compare it to the characteristics of the cutting device, which gives us a result like this. So this is actually the resulting cutting specs, taking everything into account. What we achieve here is that instead of eating out 60 dBs just for properly reproducing the whole frequency spectrum, we go down to 21 dB. So within 21 dB, we can represent the whole frequency spectrum, which is good, because if we imagine that we maybe need another 20 to 40 dB in order to have some dynamics, this technique gives us the possibility to do it. Now, having said that, we can try to mix and match the different technologies just to understand what is correct and what is not. So I've set up a list of combinations between cutting device and playback device. You know, the cutting device is always on the left-hand side, the playback device on the right-hand side. So how to get a correct flat response at playback? If we cut with a velocity-sensitive device without pre-emphasis, we need to play back with a velocity-sensitive device without the emphasis. Same thing if it's with pre-emphasis. If it's with pre-emphasis, we need to play it back with the same or a similar de-emphasis. Or the other option is if we cut a groove with an amplitude sensitive device, we should play it back with an amplitude sensitive device again. Now, it is also possible, of course, to get a wrong, uneven response at playback, which brings us to the other examples. Velocity without pre-emphasis against velocity with the emphasis is wrong. The other way around is also wrong. Velocity with or without pre-emphasis read with an amplitude-sensitive device, such as an optical device, for example, is wrong or is wrong. It's not wrong. It's simply not flat. And the other way around, same thing. But we get a wrong, uneven response at playback too if the de-emphasis do not match the pre-emphasis. If it's cut with a RIA pre-emphasis and we read it with a, called Columbia 1925 de-emphasis, we get a wrong frequency spectrum. We also get a wrong frequency spectrum if we apply any known phono or the traditional electrical de-emphasis curve to the output of an amplitude sensitive playback device. What I'm saying is just if we take Irene or visual audio, just to mention the most common optical retrieval systems, and at the output of these two systems we apply any, doesn't matter which one, any phono, so-called phono pre-emphasis, de-emphasis curve, the result is wrong. Simple as that. So, as you can see, it is unfortunately easier to get a wrong, uneven frequency response than a correct one, than a flat one. Doesn't matter whether you're using, state-of-the-art equipment, as I shown at the beginning. So that brought us to do some analysis and design, because we wanted not just to investigate how it works, but we wanted to find a solution for that. In particular, because we are the developer of one of these optical retrieval systems, we wanted to have the possibility to apply a correct equalization curve to the output of our system, which was not the case. So these are all the questions that we asked ourselves, and we basically answered all these questions, starting to draw curves, taking measurements at the output of a phono preamp, for example. We did a lot of things. We took a lot of numbers, we put them into formulas, into charts, into spreadsheets, and we finally came out with some kind of a solution. So the next step was to define whether it is better to design as an equalization device a hardware or a software component. My personal opinion is I really would like to see a hardware-based system, an analog-based system, for example, but it's not so easy to meet all the specs. So we went with a software solution in the digital domain because it's easier, not because it's more accurate. It's simply easier. We've been looking around if there's anything on the market that meets all our needs, not just part of it, because there are products on the market that meet part of it. No, I haven't found any. So I made contact with several software vendors specialized in this area, trying to sell them the idea of developing some sort of a, let's call it universal de-emphasis tool. But the point seems to be that all the part of them already have the capabilities or some kind of tools that could do that. They are probably not willing to dig too much into it because our market is a niche market. It doesn't bring money. So we've been investigating also on what reference material is available on the pre-RIA equalization. There is plenty of stuff, plenty of good stuff, but there is unfortunately also plenty of wrong stuff. So how do you know? How do you know if the information you get is wrong or right? I shouldn't do this example, but anyway, let's take a booklet that's called maybe the Bible for re-recording engineers, which is YASA TC04. I'm a member of the technical committee of YASA, so I take all my but there are tables in this booklet, page 48, 49, that region. If we look at the tables, at the values, entered there for the turnover, for the roll-off, and this information, very basic information, at least half of them is wrong, and it's an official publication. It's not just something that you find on any internet site. So we also asked ourselves whether there is or there is not a way to prototype such a solution using in-house skills. I'm lucky enough to have sound engineers working in my department as well as IT guys. So we have developed a little tool that does all the calculations, at least, for any combination. Velocity, amplitude, with pre-emphasis, without pre-emphasis, with a 6 dB slope or a 3 dB slope, whatever you can think of. And we also try to implement that using out-of-the-box tools. Out-of-the-box tools to me means if you have something such as WaveLab, for example. WaveLab, from version 9, if I'm right? If I remember well, includes an equalizer called CurveQ, which is produced by Voxingo. And if you just load a CSV into that tool, you can simulate any kind of de-emphasis curve, which is, I'm not saying it's perfect, but as a prototype, it works. If we want to show the solution to specialized software vendors, this is the solution. It has to be just finished a little bit, but it really works. So I'm running out of time. I'm probably already out of time. So at the very end, I will just play a couple of audio samples. The same record, the turntable with analog de-emphasis, with digital de-emphasis calculated and produced with our tool, and the same thing with visual audio. The same record captured with an optical system and with a digital de-emphasis applied, but the correct one. I mean, the right one for optical playback systems. Of course, I took information from a lot of different people. There are references. I mention here IASA TCO4. It's still a good booklet. Don't pay attention to the tables that mention equalization curves. I'm sorry about that, but we'll fix that. Now, some samples. I had to improvise a little bit because of these troubles we had. But now I hope I can play these examples. Okay. You see what? This is again technology. So let's try with this one. So this is the record. This is flat without the emphasis. Now the same thing with analog de-emphasis. The same with the digital de-emphasis. This one is with an optical retrieval system, just flat, without the emphasis. Well, the background noise comes from the system. I'm sorry about that, but this is one of the limits of the optical retrieval. If you notice the content, I know it's not very easy to make a distinction between the noise and the content, but the equalization applied is very, very, very similar to the one that we heard when we're playing the same, or when playing back the same record with the turntable. So what I'm saying is that the calculations are right. It works, we can do it. Now the only thing missing is somebody, software vendor or hardware vendor, that wants to implement as an additional set of parameters, for example, what we have calculated. That's it. Thank you very much.